Let's try to formulate the curl of E, electric potential, Poisson's and Laplace's equations, and do some numerical problems in this tutorial on electrostatics. The curl of E. We'll try to calculate the curl of E by first considering the simplest possible configuration, that is a point charge at the origin. So here at the origin, we have a point charge Q. Now the electric field that is generated by this point charge is E equal to 1 over 4 pi epsilon 0 Q over R square, which is directed along the R hat direction, that is the radial direction. We shall now consider 2 points A and B. Now we want to calculate the path integral of this electric field in going from point A to point B. The path integral is integral A to B E dot dl, which is equal to 1 over 4 pi epsilon 0 integral Q over R square times R hat dot dl. In spherical coordinates, this line element dl is given by dr r hat plus r d theta theta hat plus r sin theta d phi phi hat. And when we take the dot product of r hat with dl, we are left with only the first term, that is dr. So this gives us the line integral from A to B E dot dl as equal to 1 over 4 pi epsilon 0 integral Q over R square dr. And this is equal to negative of 1 over 4 pi epsilon 0 Q over R from RA to RB. That is the position vector of point A and the position vector of point B. And this turns out to be equal to 1 over 4 pi epsilon 0 then Q over RA minus Q over RB. Now, if the integration is over a closed path like this one, in that case RA will be equal to RB. And hence we have the closed integral E dot dl equal to 0. But by Stokes' theorem, closed integral E dot dl is equal to surface integral del cross E dot dA. And from this, we have closed integral E dot dl equal to surface integral del cross E dot dA, which is equal to 0. And this result gives us del cross E equal to 0. That is, the curl of the electric field is 0. And this equation indicates that the electric field is an irrotational vector field. And this equation holds perfectly for any arbitrary choice of coordinates and also for any position of the charges. If we have many charges, as you see in this figure, the principle of superposition states that the total field is a vector sum of the individual fields. That is, the total field E equal to E1 plus E2 plus E3 plus etc. Where E1 is the field that is produced by Q1 alone and E2 is the field that is produced by Q2 alone and E3 is the field that is produced by charge Q3 alone. This indicates that del cross E equal to del cross E1 plus E2 plus E3 plus etc. When we expand, this will be del cross E1 plus del cross E2 plus del cross E3 plus etc. And this will be equal to 0. We are now in a position to discuss about the electric potential. Let us consider the line integral of E from point A to B. This is point A and this is point B. Let us consider two paths, that is path 1 is shown like this and path 2 is shown like this. The line integral of the electric field from point A to point B will be the same for all paths from A to B. Why is it so? Because if it is not the same, then the closed integral E dot dl will not be equal to 0. And because the line integral is independent of the path, we can define a function Vr equal to negative of integral starting from some reference point O to the point R, then E dot dl. Here, O is some standard reference point and we are measuring the function V at point R. And this is called the electric potential. Now, how do we define electric potential? To define the electric potential, we need to have a unit charge that is placed at the reference point O. Some amount of work need to be done to move this charge from the reference point to point R. If the force that is felt at this point due to the electric field is Q times E, then the external agency must apply a force Fx equal to negative Q times E to move the test charge from point O to point R. And we define the electric potential as the force that must be done by an external force acting against the electric force to move a unit charge from point O to point R. The external agency must supply a force Fx equal to negative of Q times E to balance the electric force F equal to Q times E. And that is the reason for this negative sign in the expression for Fx. Now the unit of potential. The force is always measured in newtons and the charge is measured in coulombs. And therefore the electric field is expressed in terms of newtons per coulomb. And accordingly, the potential is Newton meter per coulomb, or this is equal to joule per coulomb. And 1 joule per coulomb is known as 1 volt. Now we define the potential difference between 2 points A and B as VA minus VB, and this is equal to negative of integral 0 to B E dot dl plus integral 0 to A E dot dl. And this is equal to negative of integral 0 to B E dot dl minus integral A to 0 E dot dl. And this can be written as negative of integral A to B E dot dl. That is, the potential difference is VA minus VB equal to negative of integral A to B E dot dl. Now let us try to formulate the relationship between E and V in terms of the del operator. For that, we make use of the fundamental theorem for gradients. From the fundamental theorem of gradients, we can write VB minus VA as equal to integral A to B del V dot dl. And this is equal to negative of integral A to B E dot dl. And this is true for any points A and B. Hence, the integrands must be equal. Or from here, we'll get E as equal to negative of del V. And this is the differential version of the potential equation. And this says that the electric field is the gradient of a scalar potential. We shall now try to solve problem 11. One of these is an impossible electrostatic field. Which one? And here K is a constant with appropriate units. We are given the mathematical equation for two electric fields E1 and E2. So let us consider the part A. When we take del cross E1, this is equal to K times x hat, y hat, and then z hat, then dou over dou x, dou over dou y, then dou over dou z. And this is xy, 2yz, and then 3zx, and then the determinant notation. So this gives us k times x hat 0 minus 2y, and then y hat 0 minus 3z, and then z hat 0 minus x. We see that del cross E1 is not equal to 0. This indicates that E1 is not an electrostatic field. Let's do the same operation with the second electric field, that is E2. And in that case, we have del cross E2 as equal to x hat, y hat, z hat, dou over dou x, dou over dou y, and then dou over dou z, y square 2xy plus z square, and then 2yz determinant. And when we calculate this determinant, it will be equal to 0. Hence, E2 is a possible electrostatic field. Alright, so E2 is a possible electrostatic field. Now, calculate the scalar potential V. We'll calculate the scalar potential by making use of the path integral E dot dl. That is, the scalar potential V is equal to negative of integral E dot dl from O to R. So let us fix the reference point at the origin, and let us assume that we want to calculate the electric field at point x0, y0 and z0. We'll consider a path from the reference point O like this. We go along the x direction first and then proceed towards the y direction, and then finally we move towards the z direction. Let us call this as path 1 and this as path 2 and this as path 3. So when we calculate E2 dot dl, this will be equal to k times y square x hat plus 2xy plus z square times y hat plus 2yz z hat dotted with dx x hat plus dy y hat plus dz z hat. So this is dl in the Cartesian coordinate system. And when we take the dot product, we are left with k y square dx plus 2xy plus z square times dy plus 2yz times dz. So this is our starting point, and we will now try to apply the line integral for all these individual paths. That is, we will calculate the line integral for path 1, line integral for path 2, and that for path 3, and finally add these all together to find the total scalar potential V. Okay, so for path 1, we see that x changes from 0 to x0. And for path 1, y equal to z equal to 0. And from this equation, we have dy as equal to dz as equal to 0. And when we insert all these values into the line integral E dot dl, this will be equal to 0. Now let us consider path 2. We know that for path 2, x equal to x0 and y changes from 0 to y0 and z is 0, and from this we have dx equal to dz, that is equal to 0, and the line integral E dot dl is equal to k times 2xy plus z square dy, and this is equal to 2k x0y then dy, and therefore when we calculate the line integral for path 2, that is integral E dot dl, this is equal to integral 0 to y0 k times x0 y dy, and this is equal to k times x0 y0 square. And for path 3, we have x equal to x0, y as equal to y0, and z changes from 0 to z0. And from here we have dx equal to 0 and then dy equal to 0. And E dot dl will be equal to 2kyz dz, that is equal to 2k y0 z dz. And when we calculate the line integral for path 3, this will be equal to 2k y0 z dz, and this is equal to 2k y0 z0 square. So we have calculated the line integral for the 3 independent paths. And the scalar potential V is the sum of all these individual path integrals, or integral 0 to x0 y0 z0 E dot dl equal to integral for path 1 E dot dl plus integral over path 2 E dot dl plus integral over path 3 E dot dl. And this is equal to 0 plus k x0 y0 square plus k y0 z0 square, and this is equal to k times x0 y0 square plus y0 z0 square. And the scalar potential is given by Vx0 y0 z0 equal to negative of integral 0 to x0 y0 z0 times E dot dl. And this is equal to negative of k x0 y0 square plus y0 z0 square. Or in general, Vx y z is equal to negative of k times x y square plus y z square. We can definitely check the validity of the potential that we have just calculated. For that, we'll make use of this expression, that is E equal to negative of del V. So this is equal to negative of x hat dou over dou x plus y hat dou over dou y plus z hat dou over dou z times negative of k x y square plus y z square. And this is equal to x hat dou over dou x of k x y square plus k y z square plus y hat dou over dou y, the same term, and then z hat dou over dou z of the same term. And when we calculate this, it will be equal to k y square x hat plus 2xy plus z square y hat plus 2y z z hat, which is our starting point. Let us now try to understand whether the potentials also obey superposition principle like electrostatic forces and fields. The original superposition principle returns to a force on a test charge Q. It says that the total force on the test charge Q is the vector sum of the forces due to all the individual source charges. That is, F equal to F1 plus F2 plus F3 plus etc. Where F1 is the force due to charge Q1 alone, and F2 that due to charge Q2 alone, and F3 is that due to charge Q3 alone. When we divide this equation throughout by Q, that is F over Q, what we will get is the total electric field, and that is equal to E1 plus E2 plus E3, etc. Now, when we integrate from a common reference point, let us assume that this is the reference point O to point R, it follows that the potential also satisfy the superposition principle. That is, the total potential will be equal to V1 plus V2 plus V3, etc. That is, the potential at any given point is the sum of the potentials due to all the source charges separately. Note that this is an ordinary sum, not a vector sum. Problem 13. Find the potential inside and outside a spherical shell of radius r that carries a uniform surface charge. Set the reference point at infinity. The problem is depicted here. We have a reference point that is set at infinity. Now we are to find out the potential inside and outside a spherical shell of radius r that carries a uniform surface charge. Let us assume that the inside or the outside point is represented by small r. From the Gauss's law, the electric field outside is given by E equal to 1 over 4 pi epsilon 0 q over r square r hat, where q is the surface charge on the spherical shell. We have also seen that the electric field inside the spherical shell is 0. For points outside the sphere, that is small r greater than r, the potential is given by Vr equal to negative of integral starting from the reference point to the point in question, that is integral O to r E dot dl, which is equal to negative of integral from O to r E r hat, then dot dr prime r hat. Let us assume that an elemental radius vector is dr prime, or this is equal to 1 over 4 pi epsilon 0 starting from reference point O to r q over r prime square dr prime, and this is equal to 1 over 4 pi epsilon 0 q over r prime with the limits starting from infinity to r, and this is equal to 1 over 4 pi epsilon 0 q over r. So this is the expression for the electrostatic potential for a point outside a spherical shell of radius r. For the potential inside the sphere, we have r less than r. And in order to calculate the potential inside the sphere, we have to break the integral into two pieces. And we have to evaluate the integral in each region using the field that exists there. This is because the potential that is inside the sphere is sensitive to what is going on the surface of the sphere. Also, in the case of potentials, infinity is the reference point. So this is a reference point. And therefore, the potential can be written as equal to negative of 1 over 4 pi epsilon 0 starting from infinity to r, that is the surface of the sphere, and then q over r prime the whole square dr prime. So that is the first part. And the second part starts from r to the point r, which is inside the sphere. And in this case, we know that the electric field is 0, dr prime. When we integrate, this is equal to 1 over 4 pi epsilon 0 q over r prime, and the integration limit is from infinity to r plus 0. This is equal to 1 over 4 pi epsilon 0 q over r. Notice that the potential is not 0 inside the shell, even though the field inside the shell is 0. And V is a constant in this region, so that del V, when we calculate, which is equal to E inside, and this will be equal to 0. The previous problem was to find the potential inside and outside a uniformly charged spherical shell. Now, problem 14 is to find the same in the case of a solid sphere whose radius is r and whose total charge is q. And we are to use infinity as the reference point. In this case, the potential Vr will be equal to negative of, starting from the reference point to r, E dot dl. And this is equal to negative of, the reference point is infinity, to r, E dr. For r greater than r, Vr is equal to negative of integral starting from infinity to r 1 over 4 pi epsilon 0 q over r prime square dr dash, and this is equal to 1 over 4 pi epsilon 0 q over r. And for r less than r, remember that this is a solid sphere, we'll split the potential into two as in the previous case. So the first integral starts from infinity up to r, and in that case the electric field is 1 over 4 pi epsilon 0 q over r prime the whole square dr prime. And the second integral starts from the radius of the sphere up to a point inside the sphere r, and in that case the electric field is 1 over 4 pi epsilon 0 q over r cube times r prime dr prime, and this is equal to q over 4 pi epsilon 0 1 over r minus 1 by r cube times r square minus r square over 2, which is equal to q over 4 pi epsilon 0 1 over 2r times 3 minus r square over r square. So this is the potential inside and outside a uniformly charged solid sphere. We now come to another important aspect in electrostatics, the Poisson's equation and the Laplace's equation. We have electric field as given by negative of del V. When we take the divergence of E, this will be equal to del dot del V, and this is equal to negative of del square V, and this is again equal to rho divided by epsilon 0. And from this we can write del square V equal to rho over epsilon 0. And this equation is known as the Poisson's equation. In regions where there is no charge, we have the charge density rho equal to 0. In that case, the Poisson's equation reduces to del square V equal to 0. And this equation is known as the Laplace's equation.